Okay, so hi, welcome back to Alan's lecture on a practical guide to quantitative finance interviews. Today, we are going to talk about linear algebra. It is extensively used in applied quantitative finance because of its role in statistics, optimization, Monte Carlo simulation, and also things like signal processing. And not surprisingly, it's actually a super comprehensive mathematical field that actually can go super deeper and can cover a lot of topics. Today, I'm trying to go through several important topics that have significant applications in quant interviews and numerical methods. And maybe I hope it could warm you up for your upcoming interview preparation. So first, it's vector. So for the vector, let's first go through some basic concepts. The first one is the inner product, or we can call it dot product. The inner product of two Rn in the space of reality numbers, vectors, x and y, is defined as the product of all its elements in the same sequence I, okay? So we can basically write it as xty. Basically, if we have x1, x2, x3, 3 multiplied by 1 matrix, and another one is also y1, y2, y3. Yeah. And if we want to have y with what? yt, right? And it is going to be the same as the left-hand part. An important thing about it is the Euclidean norm. The Euclidean norm is basically telling that if I take the inner product of x with itself, okay, xtx, and then this value is going to be like this, okay. And the angle between these two vectors, let's say this is x and this is y, right? This angle theta here can also be calculated by this way. First, we calculate the numerator, which is the inner product of x and y. And on the denominator, it's basically the product of x norm and y norm. And basically this, by taking this fraction, we are trying to normalize the length of x and y, the length of the vector to 1, right? So that this will become the cosine theta. And if it is equal to 0, then it means they are orthogonal, 垂直. And the correlation coefficient of these two random variables can also be viewed as a cosine of the angle. Okay, now let's see a real application. There are 3 random variables, x, y, and z. The correlation between x and y is 0.8. And the correlation between x and z is also 0.8. So what is the maximum and minimum correlation between y and z? Well, so how shall we think this question? Basically, when you see 3 random vector variables and you see correlation, you want to convert it from correlation to cosine theta. Why is this the case? Because if we convert it to an angle, then we can solve it use a geometric method, which means we can put x, y, z as the 3 lines which could form a triangle. Let me first draw a picture. So we already know that the correlation between x, let's call it x, and y, okay, let's call it theta. So this correlation, cosine theta, is 0.8. And between x and z, it's also 0.8, right? So which means this is also theta. So which means these 2 lines are equal, okay? And let's think up about some middle school math about the geometry. So you can see here, if I just set this line as 1, and how can we solve this problem? I know the cosine theta is 0.8, so this is going to be 0.8, right? And this is also 0.8. And now I'm asking what's the maximum and minimum correlation between y and z, okay, between y and z. So the thing we could deal with this problem. But before we try to solve it, I mean, I want to ask one question. Is this triangle possible? Well, I mean, it is possible, but we can also draw the picture in this way, right? We can say this is X, this is Y, and this is Z, okay? And this is theta, and this is also theta. We can also form a triangle like this. Let's calculate it first way, okay? Let's call it 1, and let's call it 2, and this is also 1. And we know this is 0.8, so this is going to be 0.6 and 0.6. Then we can see if Y and Z are in the same direction. In the extreme cases, you know, when this angle, let's first count to the first cases. And what's the minimum? You can see that and the maximum. So let's see the Y and Z, this angle can become smaller and smaller. And what's the extreme case? The extreme case is that Y and Z are on the same direction. Right. And in that case, what's the correlation between Y and Z? Basically, it's going to be 1, right? Because basically they are the same thing. And now the problem comes to the minimum correlation. Then for the minimum, we know the cosine theta is actually a decreasing function. Of theta, when theta is come to 0 to pi, right? It's a decreasing function. And we know this theta cannot be larger than pi. It cannot be larger than 180 degrees. And then let's come to the second cases where we are basically calculating the cosine of 2 theta, right? And I wonder if you still remember that there is a formula. Cosine 2 theta is just cosine theta square minus sine theta square, which in our cases is just 0.8 square minus 0.6 square, which is 0.28. And this is the minimum. And you may ask the question that, hey, why cannot the minimum comes from here, right? So I'm going to answer why it cannot come from here. Because if we want to have the minimum correlation, then we want the theta to be as large as possible, right? And in that case, you can see that for this method, we already set this as 0.8. And this is only can be 0.6. And if you use the Pythagoras theorems, which is just a 勾股定理, we can set this as length of 3, this is 4, this is 5. And the length of this theta has been fixed. And by some calculation, you can see this theta 1 here is going to be smaller than this theta 2 here, okay? So I want to remind you that always remember there could be 2 formats. One is that looks like this, and another one is that they can form a triangular in this way, okay? It's like an umbrella, right? It's like an umbrella, okay? So now let's come to the next topic. I think we have know enough about the vectors. Is the QR decomposition. I think decomposition is actually one important concept when it comes to linear algebra. Basically, you have the QR decomposition, you could have the eigenvalue decomposition, you can have the singular value decomposition, and you can have the LU decomposition, Chiklovsky decomposition, basically a lot of types of it. And so we need to start with the most fundamental one, which is the QR decomposition. It means for each non-singular n multiplied by n matrix A. So what is non-singular matrix? The non-singular matrix is basically first it needs to be a square one, okay? So which means it must be n multiplied by n. And the rank of the matrix should, and basically one of the simple way to determine that is that A negative 1 exists. So its inverse matrix exists, okay? For each non-singular matrix, there is one unique pair of orthogonal matrix. Then what is orthogonal matrix? Again, orthogonal matrix is basically saying that the transpose of this matrix Q is going to be the same as its inverse matrix. I think if you have done some kind of manual matrix calculation, you are going to know how powerful this is, right? Because it's super hard for you to calculate the inverse of a matrix from scratch is by hand, especially when its dimension is not that low, right? Not 2 multiplied by 2 or 3 multiplied by 3. But transpose is easy to find, right? You just need to convert it, change the direction of the sequence of the elements within the matrix. Okay, and another part is an upper triangular matrix, which means that we have a matrix, but only this part has elements. And all these elements are on the diagonal part, it's going to be positive. And we can say that A can be decomposed into Q multiplied by R, okay? And this is quite useful to solve a linear system Ax equals B, because we know we only have the upper triangular here. And for the last row, we are going to have something like xn equal to some constant, right? And this is going to be xn minus 1 plus some kind of xn, right? Like A plus B equals to C1, let's say. And because by the last row, we already know xn equals this, we can just put the value of xn into that, and we can solve xn minus 1. And we can go this back forward until the first line to solve all the elements in this matrix. And it is going to be quite fast and convenient. If you calculate the complex, it's going to be a linear one. Okay. To calculate the complexity, it's going to be a linear one. And now the question is that if the programming language you are using does not have a function for the linear least square regression, how will you design an algorithm to do so? So this is basically just trying to check with you if you know about the linear regression's mechanism. So what is linear regression? Basically, we have something like yi, right? For each y, it is going to be like multiplied by beta 0, which is a parameter. Have a xi0 plus beta 1 multiplied by xi1, and all the way to beta p minus 1 xi p minus 1 plus an epsilon I, which is the noise item, also the air item. And we can write it into a matrix format, which is the big Y equal to the big X multiplied by the big beta plus epsilon, where I is actually equal to Y1, Y2, all the way to Yn, the transpose, which is going to be a multiplied by 1 matrix. And X is also X is going to be super large. So basically this is X1, X1, 2, oh, this is 0, let's say. This 1, X1, 2, all the way to X1 minus P minus 1, okay? And this is going to be X2, blah, 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 X2, 0, and this is going to be what? Xn, 0, okay? This is a n multiplied by P matrix, and we also have the beta, which is just beta 0, beta 1, all the way to beta P minus 1. In total, there are P1 multiplied by P, right? Beta transpose, okay? And the epsilon is basically the same as Y, okay? Epsilon has the same format as Y, okay? Also, n multiplied by 1 matrix. And to find the beta, to find the least square, we're actually trying to minimize beta, which is trying to minimize the epsilon here, equal to minimize Y minus F beta, right? And it is the least square, so we're actually taking the square of that. And now let's try to solve it. This Y minus X beta, that's both Y minus X beta, right? If we take the derivative, let's call it X beta. Then the first order derivative is going to be QX transpose Y minus X beta. I think to take the derivative of a matrix is basically quite similar with taking derivative of just some random variables. It's the same, okay? And that's why we're going to find that we let this one, let the first order derivative to be equal to 0. And then we can have xtx data equals to xty, right? And if we know everything, if we have a super good computer, then that's it. We just need to put in the x and y to let it give us this best beta. Especially if your language, the programming language, has a function for matrix inverse, then this beta hat is just xtx inverse matrix multiplied by xty, right? But if our language is poor, right? We don't have that kind of coding ability or that kind of coding function. Then what can we do? That's basically when QR computation comes to our hand. This xty can be regarded as some kind of constant b, right? Some kind of constant, because it's known. It can be calculated easily. And we just need to put xtx, which must be a non-singular n multiplied by n square matrix. So we can decompose it then into a Q and a R. And remember the upper triangular magic, right? So we just need to multiply this orthogonal one with this upper triangular one to get it equal to B and to solve all these equations one by one, okay? And since we have been talking about the linear least square regression, which is a super common statistic question in interview, I also want to go through its basic assumptions here. So the first one is that the relationship between y and x should be linear. Of course, in reality, we can just guess that, and not a lot of things are perfectly linear. Not a lot of things relationship are perfectly linear, but it's just assumption. At least there should exist a linear relationship to some extent. And the second thing is that the expectation of the epsilon item is going to be 0 for all of it. And the variance is going to be a constant. And the correlation between each error item is going to be 0. So uncorrelated errors, okay? And there should be no perfect multicollinearity. What is multicollinearity? Multicollinearity means that, let's say, our x, right, is formed by x1, which is a multiplied by 1 vector, and x2, x3, all the way to xp, okay? And if, let's say, x3 equal to some kind of combination of x1 plus x2, then there is multicollinearity, okay? Then it means the correlation between some xi and j is going to be +1, -1, right? Then that's not good, okay? Basically, we can just reduce the rank of it. And last but not least, the error item epsilon and all xi should be independent. The noise should not be related with our observations or the data points. But if they are not independent, what can we do? We can do a two-step OLS, okay? It's an advanced topic in econometrics. And if you are interested, feel free to Google it or Baidu it, okay? And now let's come to our third topic, which is determinant, eigenvalue, and eigenvector. So first, for the determinant, let A be a multiplied by n matrix. It doesn't have to be non-singular, and it has all the elements. And this data is going to be follow the formula here. I know it looks bad, right? It's not so intuitive, so I'm going to write it down. Let's first consider the 2 multiplied by 2 cases, okay? Oh, by the way, this 5p can only take 1 or -1. This is order in even, okay? If this p can be converted to the natural order by even numbers of exchanges, and this is order in odd number, okay? But let's forget about that. I don't think it is going to bring you any intuition. So let's first think about 2 multiplied by 2 matrix A, B, C, D, okay? And then the that is just what? It's just these two, this diagonal minus the diagonal, the product of this diagonal. Okay, so this is going to be AB minus BC. And how about the third case? So it's somehow like something like this. Do you still remember this recursion function is equal to some kind of A F2 plus B? Okay, so if we have a third cases, A, D, then B, C, D, F, G, H, I, then it's that. It's just we first circle this one out. We first circle A, and we are going to go for this diagonal, right? And so we multiply this A with this submatrix, which is a 2 multiplied 2, and we are going to apply the same method. So which is going to be what? And then we select this B with what? With a matrix of DG and FI, and we are doing the same thing. Okay. And last but not least, we are trying to go for C and D, E, G, H. Okay. So basically, it is just A, E, F, H, I plus B, D, G, F, I. This is a that. Okay, this is a that plus C and D, G, F, I. Okay, cool. And for 4 multiplied by 4 matrix, it's the same. We just reduce it 1 by 1 to a 3 multiplied by 3, and then 2 multiplied by 2 matrix. Okay, multiply. And there are some property. Okay, there are some property. So that A transpose is going to be the same as that A, and that AB are separable to be that A multiplied by that B, and that A's inverse matrix is going to be 1 over that A. Okay. And now let's discuss eigenvalue. So if A is an n multiplied by n matrix, a real number lambda is called an eigenvalue if there exists a non-zero vector x in Rn space such that Ax equal to lambda x. Okay, and this lambda is going to be called eigenvalue, and this x is going to be called eigenvector. So the idea is quite simple, but it is actually quite crucial concepts, because it gives the foundation of things like Markov chain, principal component analysis, ordinary differential equations, right? All its importance are linked with eigenvalues and eigenvectors. And to try to find that, we are trying to solve a characteristic polynomial of the matrix A, which is the equation of that A minus lambda I equal to 0. This I here is just an identity matrix. What is identity? What is an identity matrix? It's just something, all elements are 0 except this diagonal, okay? And on the diagonal is 1, okay? So lambda multiplied by I is basically making this matrix lambda, 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 lambda on the diagonal. Okay, cool. And by the way, a matrix is diagonalizable. Okay, we call A if it is diagonalizable if and only if it has linearly independent eigenvectors. So, which means that there is no linear combination between all the eigenvectors. And in that case, A can be written as x dx minus 1, where this d here is just lambda 1, lambda 2, lambda 3, lambda n on the diagonal with all the 0, just like this one. Okay. And now let's come to the problem here. So if matrix A equal to 2, 1, 1, 2, what are the eigenvalues and eigenvectors of A? Well, the question is not that hard, But the thing is that I want to show you all the three methods you could use to solve this problem. The first one is just to use the definition of eigenvalues and eigenvector. So we set the eigenvector as x equal to x1, x2, okay? So that ax is going to be 2, 1, 1, 2, x1, x2, which is going to be what? 2x1 plus x2, and this is x1 plus 2x2. It is going to be lambda x equal to lambda x1, lambda x2. Okay. And then we can have two equations, which is 2x1 plus x2, x1 plus 2x2 equal to lambda x2. This is equal to lambda x1, right? So let's call it 1, let's call it 2. So by 1 minus 2, we're going to have x1 minus x2 is going to be the same as lambda x1 minus x2, okay? Then in that case, we could have x1 equal to x2, right? To make them equal, we can have x1 equal to x2. Then in that case, we are going to have lambda equal to 3, okay? So how can we, because we can just change this one into x1 and lambda has to be 3. And the second case by 1 plus 2. And combining x1 not equal to x2, what are we going to have? X1 equal to negative x2, and lambda is going to be 1. And the eigenvector in this case is going to be 1 over square root 2, 1 over square root 2. And the eigenvector in this case is going to be 1 over square root 2 and negative 1 over square root 2. Okay. Now let's come to our second last topic, the positive, semi-definite, and definite matrix. So 1A is a symmetric n multiplied by n matrix, as in the cases of covariance and correlation matrix. So what is symmetric, which means the lower triangular part are the same with the upper triangular part, right? They are just like flipping left-hand side to the right-hand side, with the center as a diagonal line. So all the eigenvalues are real numbers, and all eigenvectors belong to eigenvectors are orthogonal. And these conditions makes it positive semi-definite. So in that case, xTax should be larger than or equal to 0 for all vector x. And all eigenvalues are non-negative, and all the upper left submatrix have non-negative determinants. And let's just compare this semi-definite with the definition of the definite matrix. So with this one, it's changing from larger and equal to only large, okay? And this one is from non-negative to positive. And the third one is also from non-negative to negative. And all other parts are the same. And there is one way to test this question. This is related with the correlation matrix. But because correlation matrix is just a super classic example of a positive semi-definite matrix, because the correlation between two items cannot be smaller than 0. And basically, we are trying to use this kind of property. And we have 3 random variables, x, y, and z. The correlation between x and y is 0.8, and x and z is also 0.8. Remember, in the previous section, I'm trying to solve this problem with the triangular geometric method. But we can now using a classic matrix way, right? So let's write down the correlation matrix. 1, 1, 0.8, 0.8. This is x, x, y, z, y, z. And we can have the determinant P is something like And we don't, oh, sorry, for these two we are unknown, right? This is row here, sorry, this is row. And we can have a determined P is going to be as the method I talked before in the previous part here, right? I'm just applying this method and I'm going to jump over the mid part. You can calculate this as negative 0.28 plus 1.28 minus rho square. And we should fix this that part to be larger or equal to 0. And we can have rho minus 1 and rho minus 0.28 by the crossing over method. So basically, we are trying to smaller, less than or equal to 0. But how is that? Because this is going to be rho square minus 1.28 rho plus 0.28 less than or equal to 0. And we have 1, negative 0.28 and negative 1, right? And basically we are solving this crossing over. And then we know the range is 0.28 to 1. And we solve the question. So now let's come to the last part, which is the LU decomposition and Cholesky decomposition. So LU decomposition is basically trying to express A, which is also a non-singular matrix, as a product of the lower and upper triangular matrix. So basically, we can call LU as a lower upper decomposition. It can be used to solve Ax equals to B, the same. Why it is convenient, I have explained it when we talk about the QR decomposition. And the Cholesky decomposition is just special cases of that, because it's just a LU decomposition with the property that L is just a UT. What does this mean? This means that this A is symmetric. Okay, as mentioned here, when A is a symmetric positive definite matrix, and it needs to be positive definite. Why it is the case? Because for positive definite, we can have both L and U to be positive, all elements in L and U to be positive, right? And it's quite useful in Monte Carlo simulation. Why it is the case? We just need to see this problem. So how do I generate two normal distributions, standard normal distribution, 0, 1, random variables with correlation rho, if you have a random number generator for standard normal distribution? So how can we solve this problem? Well, maybe you already know an easy way. An easy way is just we put x1 as z1, okay? And we want it to have a correlation rho, right? And we all know that for standard normal distribution, we can write it as z1 and z2, right? So we generate two standard normal distribution, and we know z1 is independent of z2. And we can set x2 equal to 1. Rho z1 plus square root 1 minus rho square z2. How to determine the parameter? We just want to set the variance x2 equal to 1, right? And you can put this value into that. And in this case, covariance x1, x2 is going to be covariance z1, rho z1, because z1 and z2 are independent. So this part can be canceled out. And this is going to be rho, okay? This is basically a basic example of using Cholesky decomposition. But in another way, if you already know PCA, you may also come up with the idea of SVD, which we call it singular value decomposition. So we are trying to separate an N multiplied by P matrix. Okay, in this time it's not N multiplied by N. And S can be separated as U, D, V transpose, where U, this U is N multiplied by P, and B is P multiplied by P. And all these two are orthogonal, okay? And the column of the U is trying to span in the column space of X. And while the V is the column of V is trying to span in the row space of X, okay? And this D in the middle is just P multiplied by P diagonal matrix, which is called all the elements on this diagonal is going to be called the singular value. Singular value. And if the diagonal elements, let's call it square root lambda 1, square root lambda 2, all the way to square root lambda n, then this is D's square root, right? And then D, obviously, it is going to be D1 over 2 multiplied by D another D1 over 2's transpose. And then we can basically just separate X, which is what we want from the Monte Carlo simulation, and the standard normal distribution Z. If Z follows 0, 1, okay, 0, and this is 1, okay. This is a multivariate normal distribution, where Z equal to Z1, Z2, all the way to Zn. And any of them is just a standard normal distribution random variable. And this X can be mu, which is our mean, plus what? U D1 over 2 multiplied by Z. So we just need to find a suitable U and Z combination to solve any kind of X we want. Okay? So this is going to be all for our today's lecture. We have finished the whole chapter of calculus and linear algebra. It's a quite important chapter, and also and next time we are going to talking about the most important chapter for the Green Book. Basically, it's a probability theory. We are going to see our old friends, dice, coin, and cards. They are going to accompany you with all the interviews, especially all the quant interviews, and let's be prepared for that. I think we are going to spend around 1 week or 2 weeks on that. So let's work hard together. Thank you.